So now we want to prove this four function theorem. Let's recall that we have these four functions defined on the subsets of bracket n, and it satisfies the following property. For any two set A and B, if we compute these two functions, then this inequality holds. Then this inequality also holds for arbitrary collection of subsets, where if we write for collection, if we write this is nothing but the summation of all, alpha of A, where this capital A lies in this calligraphic A, which is a collection of sets. So we want to prove this. We want to first reduce this to the case where, this collection of subsets are nothing but everything. So we want to fix these two into one specific thing. How do we do it? Is that if we have this alpha, beta, gamma, delta, then we replace this with this function. Let me write it in a better way. So here if we write this for any x which is subset of bracket n, this is 1 if this x lies in this collection, 0 otherwise. So this is indicator function. We consider these functions instead. Then what happened? This relation still holds with this new function, because if we have a 0 on the left hand side, then inequality holds because these are non-negative functions. But if we have 0 on the right hand side, so one of them is 0, meaning that this set does not lie inside of here. That implies that at least one of A or B. So if one of them is 0, that means this set does not lie in here. That means this is union of two sets, and it's not in this, this collection, which is exactly, A union B, where A is in this collection and B is in this collection. That means one of A and B, either A does not belong to here or B does not belong to here. In this case, one of these becomes 0 on here. So with this new function, this inequality still holds. And with these two, if you consider the conclusion of this, theorem on here, the conclusion statement, alpha of A is same as alpha of, this function, if you consider 2 to the bracket n. So if you consider every subset, collection of every subset, these two are actually, let me write it again as a more obvious that it's calligraphic A. Then these two have the same value. So for each of these four, same relationship holds. So what we can do is by replacing this with these functions, And it suffices to show that alpha of 2 to the n, 2 to the bracket n, beta of 2 to the bracket n, gamma of 2 to the bracket n, delta of 2 to the bracket n holds. So for if this holds for arbitrary alpha, beta, gamma, delta, then if we want to fix this specific one and prove this, then what we do is we replace these functions. Instead of that, we consider this. And then for this, we know this holds. Then we are done with proving this. So it only, it is sufficient to only prove this holds for arbitrary alpha, beta, gamma, delta. So now, with this assumption, so this is what we want to prove. And we prove this by using induction on n. So what's the base case? Base case is when n is 1. So now for each, say, pi inside of these 4 functions, let's just write pi 0 as pi of empty set, and pi 1 is pi of bracket 1. Then, by using this, by using this, what we know? We know that alpha 0, beta 0 is at most gamma 0, delta 0. Because empty set union empty set is empty set. Empty set intersection with empty set is empty set. And for other combination, we have this relation. These 4 relationships. Now we want to what we want to prove is the following inequality. So now we want to prove these for n equal 1. So this becomes, there are only, when n is 1, there are only 2 elements, which is empty set or the entire set. So this is what we want to prove. So here, if gamma 1 is 0 or delta 0 is 0, then what happens? If this is 0, then we have this term and this term. Gamma 1 delta 0 and gamma 1 delta 1. So we have these two. And we know that gamma 1, gamma 1 is 0, then these are all 0, and these are all 0. So on the left-hand side, we only have this one term. And on the right-hand side, we have this term as well as this term. So this implies the inequality. If delta 0 is 0, again, what we don't know, these are 0, so these 4 are all 0. On the left-hand side, we only have alpha 1, beta 1. And on the right-hand side, because this is 0, we have gamma 1 times delta 1. So from this, we get the inequality. So we have the inequality in both cases. Otherwise what we have, so from here what we get is gamma 0 is at least alpha 0 beta 0 over delta 0, and delta 1 is at least alpha 1 beta 1 over gamma 1. So when both delta 0 or gamma 1 is not 0, then we can obtain this. So using this, let's say this star is equivalent to what? So you replace this into give me a moment. Let's not say equivalent to. Can be derived from alpha 0, beta 0, delta 0. So instead of this gamma 0, you write this. And delta 0 plus alpha 1, beta 1 over gamma 1. So if we prove this, then we obtain what we want. And by multiplying delta 0 and gamma 1, this is equivalent to, say, this inequality. Again, by computing it, you can actually check that this is equivalent to this. You can check it for yourself. Then here, what you have is give me a moment. I didn't write it correctly. So this. So what we have is these two inequality says that this is at least 0. So this proves the base case. So now we want to use induction to proceed. So now what we want to do is following. We suppose that the, say, this sharp holds for n-1. And now what we want to do is we want to prove this sharp equation for n. But we want to convert this into the equation for n-1, inequality for n-1. So how do we do it? For each phi, which is either alpha or beta or gamma or delta, and a, which is subset of n-1, we let p prime a be nothing but the p prime a plus p prime a union n. Then what do we know? Then phi of this entire subsets of bracket n is not same as this, because this is summation of all p of a, where a is in 2 to the n. No, a is subset of, give me a moment, let's write it properly. This, and the right hand side is summation of all a within n minus 1 plus all a union with n, and these two summations are obviously same. So because of this, we only have to prove the following for n alpha prime beta prime and gamma prime delta prime. But this form is exactly the induction hypothesis that we assume here. So you replace this with n minus 1 and alpha, beta, gamma, delta are arbitrary functions. But we only have to, so that's what we want. We want to invoke the induction hypothesis to conclude this. But for this, we need to actually check that these functions are the arbitrary function which satisfy this. As long as alpha prime, beta prime, gamma prime, delta prime satisfy this condition, then we can apply the induction hypothesis. So that's the induction claim that we are doing. So as long as alpha, beta, gamma, delta satisfy this, then we have this, and we assume that that's true for n minus 1. And for n, we want to check that these four functions are the good functions that satisfy this. So we want to check that alpha prime, beta prime, gamma prime, delta prime satisfies the condition. So we fix a prime and b prime, which is subset of n minus 1. And in order to check that, now we let alpha bar, beta bar, gamma bar, delta bar be functions on 2 to the bracket 1, which is nothing but the empty set and set of size 1, with the following definition. Let's write it this way. So for each, so now for this we have sets a prime, b prime, a prime union b prime, a prime intersection b prime. We have these four sets. And for these four sets, we want to check that this alpha prime and beta prime satisfy the relationship that we want. That's what we want to check. And for this alpha prime and beta prime, gamma prime, delta prime, its value is actually summation of these two functions. Its values on these two sets, A and A union N. So we consider these sets, and in order to deal with them in a more convenient way, more concise way, we designate these values with this empty set and 1 in the following way. So that later we want to use the statement of the base case that we have proved. So for all of these functions, here if you see, and every time we have an empty set, we evaluate the corresponding function on these sets which misses the last element n. And whenever we are evaluating this function on this bracket 1, we actually evaluate the function on the set which contains the last element n. So now for this alpha prime and alpha bar and beta bar, gamma bar and then delta bar, we want to actually check that these satisfy this condition when n is 1. Then, so what we want to check is when S and R are taken either as either empty set or set of size 1, then here, if you consider this an SR, so for example, if you have empty set, and this is empty set, and this is empty set, then these four functions are nothing but just alpha and beta, gamma, delta. So if you just apply this given condition, then we get this inequality. And if, say, one of them is empty set, and this is bracket 1, then this is empty set, and this is bracket 1. So you have A prime and B prime in union with n. So you take these two sets, and then you use this given condition for those two sets, then you get this inequality. So you can actually consider all four cases of this S and R, and you can actually check that this holds. Then, by using the case of n equal 1 of the statement, then this is which we already have proved. Then what we know is alpha prime of A prime and beta prime of B prime is actually same as, that's exactly union, summation of these two times summation of these two, right? So that's exactly alpha bar of 2 to the 1 and beta bar of 2 to the 1. Again, this notation is same as alpha bar of empty set plus alpha bar of bracket 1, which is exactly sum of these two, and that's the definition of this alpha prime. And because of the n equal 1 statement, this is at most gamma bar of 2 to the 1 and delta bar of 2 to the 1. And so this is actually equal. And again, by the definition of this gamma prime and this definition, this is nothing but the gamma prime of A prime union B prime, delta prime of A prime intersection B prime. So, hence, this shows that this star condition holds for alpha prime, beta prime, gamma prime, delta prime on bracket n-1. I mean, we don't need this. Anyway, so by the induction hypothesis, then implies alpha prime of 2 to the n-1, beta prime of 2 to the n-1 is almost gamma prime of 2 to the n-1 and delta prime of 2 to the n-1, and which is equivalent of alpha of 2 to the n, beta of 2 to the n is at most gamma of 2 to the n and delta of 2 to the n, 2 to the bracket n. So this proves that this holds for all n. And as we mentioned at the beginning, when we have arbitrary alpha, beta, gamma, delta, and this collection A and B, then we replace this with alpha, beta, gamma, delta with this function. Then this function still satisfies this condition, so we can invoke this to here. Then for this function, this inequality holds, which implies that this also holds. So this concludes the proof of the theorem. So we have proved this four function theorem, and it's about this structure, subsets of bracket n. But we can actually, prove the same theorem on a more general structure than just the subsets of bracket n. So in next video we will briefly explain that and then derive the FKG inequality from this function.